Scatter graphs and correlation. A scatter graph has an x-axis and a y-axis. And has a series of dots plotted on the graph. Sometimes these can be x's. Scatter graphs show how two variables can relate to each other. So, for example, on a scatter graph, we may see temperature as the x-axis and ice cream sales as the y-axis. So we would presume the higher the temperature, the higher the number of ice cream sales, and the lower the temperature, the lower the number of ice cream sales, and so on. So it's two variables that are related to each other. So in our first graph, there is what is known as strong positive correlation. So we can see that the dots in our graph are all very close together. So that's where the strong comes from. Now, sometimes in a scatter graph, we'd actually have a series of x's on the graph instead of dots. Positive means that our data is going upwards. So we can see that the dots are going uphill. So positive is going uphill or upwards. We read a graph like we'd read a book from left to right, so we can see that the dots on our scatter graph are going upwards. So that's where the positive comes from. So strong, they're very, very close together. Positive, they're going upwards. So this is known as strong positive correlation. In our next diagram, we can see that the dots are quite far apart. So they're very close together here and they're quite far apart. If I was to draw in a line known as a line of best fit, I would have all the dots close together on the graph on the left. Whereas if I was to try and draw in a line that would fit in with all of my dots, they would be all quite far apart. Some of them would be close together, but quite a lot of them would be far apart. So we have weak correlation in this graph. So strong correlation means close dots, whereas weak correlation means that they're quite far apart. But this is still positive because it's still going uphill. So both of these graphs have positive correlation because both graphs are going uphill, or the data is going uphill or upwards. But this graph is strong correlation because the data values are all close together, whereas this graph has weak correlation because they're all quite far apart. In our next diagram, we have what's known as strong negative correlation. So the correlation again is strong because all the dots are quite close together. If we were to draw in a line of best fit, we would see that most of them would be very, very close to the line. However, now our data values are going downwards. So negative correlation equals downhill or downwards. So our dots are going downwards, they're going downhill. The graph on the right is also negative because we can see the dots are also going downwards. So we read the graph from left to right, so it's going downwards. But it's weak correlation because they're not very close together. So this graph has strong negative correlation. This graph has weak negative correlation. These dots are all close together, so they're strong. These dots are quite far apart, so they're weak. But both of them are going downhill, so they're both negative. Negative correlation. In both of these graphs, there is no correlation at all. So the graph on the left, the scatter graph, is done using x's, and the one on the right is done using dots. Again, it doesn't matter which way you do it. So no correlation means that there's no shape to the graph. So It's not going uphill, it's not going downhill, they're not close together. So I couldn't draw in a line of best fit here. There would be nowhere to put it, and I couldn't draw one in over here either. So there's no correlation in these graphs. So the graph on the left, the example used here, is that the x-axis represents the distance to work, or distance from work, and the y-axis represents wages. And it makes sense that there would be no correlation between these two variables. They would not be related to each other. The distance you live from work is not going to affect your wages. There's not going to be any relationship between the two. However, if the x-axis was changed, let's say, to number of years in your job, we would expect that there would be correlation, because we would expect that your wages would increase the more years that you're working somewhere, and so on. So in this scatter graph, our x-axis represents maths marks in a test, and our y-axis represents English marks in a test. So each of the x's drawn on our graph represent a student. So for example, this student here scored approximately 32 marks in her maths test and 30 marks in her English test. This student here scored approximately 42 marks in maths and about 53, 54 in English, and so on. So what I've done is I've drawn in the line of best fit. So I've drawn a line through the data values, going right through the center of them. It's very important to note that this does not start at the origin. Now sometimes it actually might start at the origin just by coincidence, but you do not necessarily start the line of best fit at the origin. So just draw it right the way through the data values. So let's say that Jenny sat her maths test and did not sit her English test, but has to resit it. And she wants to get an idea of what mark she can presume to get in English compared to the rest of the class. Well, if Jenny scored 75 in maths, what is she likely to get in English? What we're going to do is go to our maths axis, which is our x-axis, and go to 75, and we're going to draw a line straight up until we touch the line of best fit, and then we're going to draw a line across until we touch our y-axis, which represents the English marks. And we can see that if Jenny scored 75 in maths, we can expect that she may score around 73 in English.